So I decided to skip my usual talk and instead try to cause discussions and do a demo workflow. As you know, both of those things are stuff that usually fail. So we'll see what happens. Anyway, yes. So LSST, brokers, multi-messenger programs. I like to start from this figure. It's a drawing made by Tove Jansson. Some of you might know her. She's a Finnish author. Also made nice drawing. It's showing astronomers from kind of the old school time. And you can see these guys, back then it was, of course, guys, are looking into some sort of universe that's violent, dynamic, mysterious, and slightly scary. And they are thinking and trying to find ways to understand what's going on up there. And of course, this is the almost romantic notions of astronomers that we're trying to keep. The problem is, of course, that how do we do this in this era of huge facilities that produce enormous amounts of complex data? So this is kind of background of what I'm trying to do. Basically, there's going to be 3 teams talking about Vera Rubin Observatory and the need for brokers. And then I'll have like a little sample workflow that I will try to run. And then in the end, I'll try to look ahead, and hopefully we can, based on that, think of some work topics for the end of the week. Okay. And if you have questions, just stop me. Okay, LSST, Vera Rubin Observatory. Most of you already know all of this before, but anyway, we should, for form's sake, go through it. So it will be huge, it will be great, it will be many things for a lot of science disciplines. For time domain, multi-messenger science, we can conclude something. Some things, it will characterize slowly varying transients very well with multiple bands and so on. For example, TDEs. It will be a discovery machine for young transients, for faint transients, for distant transients. But typically here, LSST alone won't be enough. You definitely will need follow-up observations while these things are alive, which is what makes these rapid response systems, the alert brokers, actually critical. And this is something you can see. This is probably a very old figure showing the survey design, but I don't think it's changed that much. And what you can see, so these are the expected number of visits for all 10 years. And you can see that for most of the sky will be something like 1,000 visits. So for all bands over all 10 years, meaning that typically for a particular point, we will hit it every few days, ideally, but then in a different band. So it will be in itself a messy data set to use. Then I will make some comparisons to Zwicky Transient Facility, which is, of course, a currently ongoing cadence optical survey designed to discover transient objects. Of course, is this thing seen? Maybe. Of course, LSST will have a much, much larger mirror. It will have much better image quality. It will have many more filters. It will go much, much deeper. At the other hand, ZTF has a wider field of view. So these are things we know. I think the main thing to take along is that this depth that we're looking at is kind of at the level where typically we won't be able to follow up these transients on normal or small scale telescopes. They will just be too faint, at least not when they're interesting. So that's one takeaway point. And then we can then compare transient detections, so detections of variable, real astrophysical events in the sky. And here we have ZTF, of course, large number, trillion, billion. Maybe the most interesting is the nightly alert rate, which can be up towards 1 million alerts. It's not quite that much, but it's that kind of order of magnitude, and a nightly data rate that's pretty large, and an alert latency of a few minutes. And then we can compare that with the expected rates from LSST. Of course, numbers are much, much larger, typically kind of an order of magnitude, but it won't be 10 orders of magnitude. In some sense, we almost already are sniffing at these sort of data volumes. And in particular, if we consider that already now with this Vicky Transient facility, we discover these 1 million alerts every night. 99.9% of those we throw away, either because they are not interesting or because we believe they're not interesting, or because we believe they're interesting, but we don't have the follow-up resources to actually figure out what's going on. And in some sense, not that much will change for LSST. We can add another 9 in this fraction of objects that we're discarding, but we're already in this regime where we're discovering much, much more variable events in the sky than we actually have resources to follow. So in some sense, we're already in this LSST era already now. Yes?
General parameter record, not the things they throw away at yet, just to see if there's a pattern of the different things.
If you define a pattern, we can search for it. To answer a little bit more specifically, yes, for example, we are regularly doing kind of general searches for supernovae to discover objects that were missed by the general searches. And yes, you always discover objects that for one reason or another were missed. It's of course hard to answer the question, did we miss anything? The question is probably yes, but the archive is huge. So you kind of have to ask the question specifically, and then you can search the archives for it. By the way, that's one of those things that I think we could do much, much better, is to search these by now huge archives of optical variability to see what's done there, especially if you go a little bit fainter. So in the bright end, most things, so people were trying to follow things, but if you go towards the fainter end of what CTF is capable of seeing, we basically have no idea what's going on there. That's thrown away. Okay, so that was kind of a little bit recap of LSST. So amazing, lots of data. And then we get to the question of brokers. So what are they? I think you've heard the term, and why are they? So I tried to schedule that here. Typically, or at least a decade ago, it would be pretty straightforward that you detected stuff, you store that information in a database, and then users could query this database, for example, events discovered in this region of the sky within a certain time range. And you wouldn't need any intervening layers with brokers adding yet another kind of technology that you need to learn. But when we get to these large data sets, this is just not feasible to keep running, just because with these large data sets and unpredictable queries by uneducated and astronomers, especially that all at once after, for example, the gravitational wave trigger would come out, this data model would just never work. So you can't have a database of real-time events that you're continuously filling with data while you're allowing anyone to query the database. So this was kind of realized, and this was then what led to the decision that this problem is going to be solved by brokers. These are brokers, as they are traditionally seen. So they decide what's the best thing to do with your stocks, for example. And kind of computationally, it's pretty easy to see why this solves the problem. Instead of having this database, you publish a real-time stream of alerts that's going somewhere, and then it's someone else's problem. So it's an easy way to solve the problem. And then you have a bunch of brokers, and they then have a connection with downtown customers or astronomers that they then provide basically to what can be a small subselection of all of those alerts. So maybe the particular interesting supernova that was interesting to this guy. So in general, this is you could say a necessary schema to manage all these data rates. And so it was kind of decided pretty early on to have a fixed set of brokers, or basically endpoints, because that's what it is, for this real-time alert stream coming out of LSST. these endpoints are what we call brokers now. So there's 6 or 7 or 8. It's a little bit hard to keep track. I don't know how many. There are some of those that I don't know how much they're operating right now. But anyway, there will be a number of endpoints. So Antares, Ample, Fink. They're also represented here. Antares, Laser, Bavamul, and Google Pit. And the idea is then that this will be endpoints somewhat distributed across different countries, probably different out times and whatnot. And that users can then connect to one of these infrastructures to get their LSST real-time data. And kind of the assumption is that you will be able to get this filtered data set based on, for example, cross matches to catalogs or some sort of classification. So ideally, Tycho would say, I want to have my supernova, and then he would get his supernova, and we would be happy. So in some sense, this is straightforward. There are, however, problems, and I'm going to focus on them because we are supposed to have discussions and find solutions here. Oh, well, this is an important point. Think about multi-messenger applications. Principally or conceptually, it's of course easy to imagine adding or doing multi-messenger science simply by providing more real-time data streams to these brokers. And then again, you get what you get in the end and what you want in the end, and the problem is solved. Okay, however, 3 kind of questions. Should we trust these brokers? Looking back into history, we can kind of tell that sometimes that was a wise decision, sometimes it was not a wise decision. Another question, so what just happened? If we're thinking about this as a flood of alerts and you do something, but in principle, the flood has already passed once you stop and think about what happened. So how do you figure out what actually happened? And what could have happened that I did not note? And another question is, so we had these fancy broker systems that I represent one of them. So will they last? Will they be around? LSST is supposed to be running for 10 years, right? And then we're already talking about ET and alerts from ET, which is even further down the road. So let me expand a little bit about those 3 questions. So who knows how to select the transients that you're interested in? And I think the only thing I know is that it's not the broker teams. I mean, in some sense, we can try to develop infrastructure, but we will never have the scientific competence and ideas of astronomers, scientists. It will also change with time. It's not that we now can define what's interesting for LSST, but rather this will be a continuous, updated process based on what we detect, theoretical development, and so on. This question of what just happened, so provenance, reproducibility. Last week, we talked about both, and especially statistics and trial functions, which will be even more critical. They're already critical. People claim X sigma detections, but reproducibility is in general hard. And typically, we ignore it just because it's hard, not because it's not important. I think we all might have suspicions on some of these numbers. And then this question of stability. I think for all of these infrastructure systems, the long-term funding picture is somewhat unclear. It's not the NASA approved mission. A lot of them have single point of failures, which in practice in our field means that there are 1 or 2 persons that have been doing a lot of development, and if they leave, what will happen? I think we don't know. And then there are no common interfaces between them, which again limits stability. So I think what I'm trying to communicate here is that brokers are really a critical element for how we're doing real-time science in the next decade. There's no way to avoid them. At the other hand, there are many questions in how to use them that we still have to resolve, and that the broker teams will not solve themselves. At least I won't. I don't know. I don't think the other will either, mainly because these are scientific questions. Okay. So then I want to say a few things about, I don't know if the European Broker Initiative is an approved name. maybe it is. So one way that we have been trying to solve this question is to at least among the European real-time infrastructures, there was an attempt to work together. And in theory, this is a very attractive scenario because basically the different infrastructures have different focuses and different expertises, and you can see that working together could alleviate a lot of these weaknesses. So we started discussions. Unfortunately, there was a big funding proposal like a year ago that was not granted. If that would have been granted, I think this would have been kind of a straightforward path. Right now, I don't know what happens, but this is, I think, something that we can discuss more this week as well. Okay. So I'm going to jump ahead and try to do this live demonstrations. We'll see how it goes. So let's see. So what I want to do is to run a full multi-messenger analysis, which means downloading some LIGO sky map, match with all CTF alerts in this region, fit a theoretical model to those, and then upload the results to this dev version of Astro-COLIBRI. This is the goal. Let's see if it works. So, and this is then how I would run this. So Humboldt, this is a local version of Humboldt, so the broker that we're developing, that basically has a schema. So this is a file that I'll show. And this is basically what it's going to do, hopefully in the background while I talk. So let's see if it's done. Okay, it's doing stuff. In the meantime. Okay, so Humboldt, again, there are the different brokers, and they, in principle, you use them a little bit differently, but the goal of all of these are the same. So I'm going to focus on this Humboldt analysis and workflow framework for high throughput time domain astronomy. And this is the file that I'm running in the background. So it's a configuration file. You can find it here. It's, of course, a bit too long to show on the screen. And most of it are configurations that are not really interesting for a user. But in principle, what it will do is to retrieve a HealPix map from GraceDB. It could also be from a link from a GCN. As you saw, you could just pipe in reading that from Kafka stream. It will retrieve all the ZTF alerts that were found within a time range close to this map. In this case, it happens to be around 25,000. Filter these for new transients, so things that were not long-lived. Match their disposition to a number of galaxy catalogs. Fit a theoretical model to the gravitational wave, to the optical light curve, and then combine all this information into one number that we can call kilonova NES. And the higher the number, the more like a kilonova this is. And then these candidates will try to post to Astro-COLIBRI. So, okay, this is just a schematic instead of a long configuration file. So each of these boxes correspond to a Python module, again, that's available online, and in principle, anyone can run them. You don't need to do that within Humboldt. And you can then use the same workflow, either listening to a stream or by grabbing an old map from GraceDB, for example. And then you have these theoretical models here that you're running. So this is a link to the POSIX sequence that some of you might have used, that in the background does these kind of fits to the data for a specific kilonova angle and so on. And then in the end, there's an output layer that, again, kind of different structure. Here we'll be looking at the Astro-COLIBRI publisher output. Okay, and then this configuration file, I was now running it locally in my laptop. The idea is, of course, that you can run this on a computer center where it's scaled, so you can run it on large batches or in real time, and also large sky regions and so on. So let's see now. Okay, so you can see that it's, again, I won't go through the logs, but you can see it finished. And I don't know if you keep track of them, but there were 4 new things that appeared. Now they have random names. So we can see, so this is the sky region. Let's see if we can look at the latest one. So you can see it was there. Now the gravitational wave outline disappeared. Why did it do that? Okay. Anyway, you can see, so this was now what was detected as a potential counterpart in the ZTF alert flow, and you can see it was reported with a specific kilonova-ness rating of 13, which makes it not so exciting. But if it would be a higher number, you can still see how you could have piped that through your telescope or something like this. Okay, so it actually worked. Let's finish this. So in principle, we not only have brokers, we have multi-messenger workflows that actually work. So this was modular. You can develop it locally and you can scale it. You can share it to someone else in a paper. They can reproduce it, and so on. And in reference to what we did before, everything in here can be directly mapped to the IVOA provenance data model. So in principle, by running this, you can immediately then transfer things to some sort of, I don't know if it would be called a workflow or what it would be called, but that mapping is there. But, and this we can get back to my kind of but question. So this all works, but the flexibility required modularity. Modularity requires abstractification, which means that it's non-intuitive for astronomers. So what it means in practice is that it's still on a level where you basically need to be an experienced user to actually develop these things. So again, we're not yet done with this development. Okay, so you can run this. I mean, if you want to try it out, there is other instructions that you can try out. Okay, so to kind of end this, I will try to look ahead. Data irreversibility, I think I already mentioned that. It will be critical. It is already critical, but since it's so hard to do, we typically ignore it. With LSST and so on, it will be even more important. Okay, so kind of my main point now in the end is for all this complex workflow and using brokers in the LSST era, the key way to actually get it to work is to invert the work order that we're currently operating in. Typically now, astronomers for 2,000, 5,000, or I don't know, 8,000 years have been doing some version of get some data or someone points it to some data and you get excited. You call someone on phone, they're also excited. And in principle, you're developing some analysis based on this. And then you conclude based on the results. And then these things, how to make this reproducible, how to scale it is very hard because this first point was very fuzzy. So what we actually need to do is to invert this process and start by defining some theoretical project hypothesis, hopefully based on some model, and then implement some workflow that can actually look for this model, this theory, and then upload this into these live broker system that can actually look for it among the live data. This is both the way to achieve provenance and the way to scale things for future surveys. The problem is that it's very non-intuitive for an astronomer. As an astronomer, you want to see the data right away, right? So this is almost more of a sociological shift rather than a technology shift. Okay, so my summary. Brokers will be a critical component of real-time infrastructure, but they will not and should not do the science. So we have to figure out how to communicate. What about the path ahead? There are some things we should do, but that are possibly impossible, especially for this week. So we should make funding agencies pay more for scientific computing. We've been saying so for many years. It hasn't happened. Maybe it happens a little bit, but it's still not clear. in principle, we could do stuff that we require publications to, so that everything that's published is also reproducible and that every piece of data is public. It would be nice. Also, probably not something we can achieve this week. So what could we achieve this week? Well, we can talk about interfaces, standards. I think we've seen repeated many times. This is something that we can actually, in small teams, start talking about. Not only for alerts, but also for filters. I would love to have a filter that you can use in any broker. Software, I would like to have an interface such that anyone can take a machine learning model and run it on some other data set, and so on. We can also talk about what workflows do we want to have running in the LSST era, combining what data sets. So starting in this inverted work order that I mentioned, and then we can together think about how to actually make them happen. And take home message to all of you to think about this inverted work order, to think about how to implement an hypothesis before requiring to have data lying around. And then start talking to the broker teams early in this process. Thank you.